In previous lessons, we solved conservation of mechanical energy problems first using variables and then using numbers. In this lesson, we're going to go through two problems just using numbers. Hopefully, you're familiar enough with the variables that you feel comfortable just going right to the numbers. So in this problem, we have a 2-meter long pendulum that hangs from a ceiling that is 3 meters above the floor. Let's put the dimensions in to this diagram where we can. We have an 8-kilogram bob, and it's released from rest, which means its initial speed is 0, at a height of 1.5 meters above the floor. And we're asked to find the speed of the pendulum bob as it swings through its lowest point. So what we'll do is take two snapshots of the system. One when the bob is at its starting point, and one when it's down there. And now we need to go about identifying the different types of energies that the system has when it's in state A or state B. Snapshot A, the bob has no kinetic energy because it's not moving. We're told that it's released from rest. It does have some gravitational potential energy if we choose the reference line to be the floor. Now, we can choose the reference line wherever we want, but since we know the height above the floor initially to be 1.5 meters, that seems like a good reference line to use. So the gravitational potential energy of this mass will be the mass times g times the height above the reference line that we chose, mgh. We have no springs to worry about, so the energies for snapshot A are complete. Let's go to snapshot B. When the bob is in snapshot B, it definitely has kinetic energy equal to 1/2 times its mass times its speed squared. In snapshot B, the bob also has gravitational potential energy because recall that we chose the reference line to be the floor level. That gravitational potential energy will be the mass of the bob times g times the height that the bob is above the floor. Now, what is that height above the floor? The answer is 1 meter, because recall that from floor to ceiling is 3 meters and that the pendulum itself is 2 meters in length, which means that if I start here and move down right there, I've moved down 2 meters, which means there's only 1 meter to go before I hit the floor. M times g times the height above the reference line. Again, no springs to worry about, and the law of conservation of mechanical energy says that if I total up these three boxes and I add up these three boxes, 1/2 times 8 times Vf squared is 4 Vf squared, and then 8 times 9.81 times 1 is 78.48. Those terms added, not multiplied. And if energy is conserved, those two quantities should be equal. So now we just need to solve for Vf. Let's subtract 78.48 from both sides. Let's divide both sides by 4, and let's take the square root. Let's try another one. We have a 0.38 kilogram object at rest on a spring with a spring constant of 6.0 times 10 to the third newtons per meter. We have our mass here. He's at rest, and he's on this little platform, and underneath it is a spring, and this spring is compressed, as you can see, and that spring has a spring constant of 6,000 newtons per meter. The original spring length is 82 centimeters, but it has been compressed to 52 centimeters. Now, we're not interested in the initial length of the spring or the compressed length. We're interested in the change in length, which you can see is 30 centimeters or 0.3 meters. And since our spring constant is in newtons per meter, our change in length of the spring should also be in meters. When the spring is released, the object goes how high? In other words, when we release the spring, this object is going to go up how high does it go? So let's define two snapshots. One when the object is down there, and two when the object is up there. In snapshot A, this object is at rest, so he has no kinetic energy. If we define where the object starts out at as the reference line, then he has no gravitational potential energy in snapshot A. But the system definitely does have some elastic potential energy when the object is down here on the bottom, and that's equal to 1/2 times k times delta x squared. Okay, so we release the spring, the object flies upward, and at the very top he has no kinetic energy. You should have learned that when an object is launched straight up, at the very top its speed for an instant is 0. That mass will have some gravitational potential energy at the top, equal to m times g times h. And of course h is what we're looking for. When the mass is at the top, the spring has now resumed its original length, so there's no more energy stored in the spring, so that term is a 0. We total up the three energies from snapshot A, we add up the three energies from snapshot B, we set them equal to each other, and we divide both sides by 3.73, and this object rises to an alarming height of 72 meters.